greetings Dr. Yo and all the viewers. We are from Group 5 will be presenting about the amplitude shift keying. As we know, in digital modulation there are three types, which are the amplitude shift keying, frequency shift keying and also the phase shift keying. And amplitude shift keying is the simplest digital modulation technique. To explain it in a simple way, amplitude shift keying, also known as ASK, is a type of amplitude modulation which represents the binary data in the form of variations in the amplitude of signals. So it's quite similar to the analog amplitude modulations, except there are only two output amplitude possible. So as we can see here, the carrier signals will combine with the discrete signals to create a modulated signals. So let's look at the ASK generation method. So the ASK modulator block diagram comprises of carrier signal generator, the binary sequence from the message signal, and the band limited filter. So the carrier generator sends a continuous high frequency carrier. Meanwhile, the binary sequence from the message signal makes the unipolar input to be either high or low. And finally, the band limiting filter shapes the pulse depending upon the amplitude and pulse characteristic of the band limiting filter or the pulse shaping filter. So let's look in a more detailed way. Okay, so the carrier signal will combine with the unipolar. So as we can see here, there are input of 1 and 0, which is known as 1 is high, 0 is for low. Okay, so the binary signal when ASK modulated gives a 0 value for low input. Okay, for low input for unipolar 0, it gives a 0 value, while it gives a carrier output for high input. High input means which is 1. So when it's 1, we can see a carrier output. So this is how the digital modulations amplitude shifting works.
So let's talk about the mathematical analysis of amplitude shift keying, that's the ASK. The voltage ASK equal to 1 plus Vm A over 2 cos omega t, where VASK is amplitude shift keying signal, VMT is equal to digital information signal info, A over 2 is unmodulated carrier amplitude info, and omega c is analog carrier random frequency. Then, when the binary input is in logic 0, Vm will becomes -1. When the binary input is 1, logic 1, the Vm becomes +1. This will result in VASK equal to A cos omega c when it is in logic 1. It is 0 when it is logic 0. And here is the graph you can see. Now, let's talk about how to generate ASK signal. It's easy, just multiply the modulating signal and the carrier signal. But remember, the modulating signal must be in binary information signal form. And here is the equations for the VMT, that's the binary information signal. And here is the carrier signal. Then just multiply both of them, you can get the VASK, that's the amplitude shift keying signal.
Hi, Assalamualaikum. My name is Fadlina Mira. Alright, so I'm gonna explain about the example of bandwidth requirement. Alright, so from the graph, we can see the minimum bandwidth and the boundaries of the graph. Alright, so the condition of the line is BW is equal to 1 plus D and bound and also D more than 0. Alright, so the example given, they ask us to find bound and minimum bandwidth necessary to pass a 10 kbps binary signal using ASK. Alright, so to search the bound and minimum bandwidth, we need to use the formula BW minimum is equal to FP equal to N. Alright, so basically N is N over 1, N is equal to 1, and FP, they already give us 10 kilo BPS. Alright, so the answer for the BW minimum is equal to 10 kilohertz. And for the N bound, the answer is 10 kilo bound per second. Okay, so basically the formula is just the same N bar and also the BW minimum. All right, for next, this slide is kind of like they tell us how that we can search for the ASK, how we want to do the ASK. Okay, so first for the ASK generation or transmission, we need to use multiplier or using on and off switch. And for the ASK receiver, we need to use envelope detector and also coherent detector. All right, that's all from me. Thank you.
So now I'll be explaining about the ASK signal generation. By using the multiplier, the message signal will go through a low-pass filter to the multiplier and multiply together with the carrier signal to be transmitted out as a ASK signal. The generation using on and off switch. When the switch is on, the message signal will go through the bandpass filter together with the carrier signal and form an output ASK signal. So for ASK receive, there's two types. One is called non-coherent detection, where there's no need for the carrier signal to be phase locked, which is equals to the carrier signal from the transmission and receiving end would be not in phase. It is a much more simpler circuit that have a higher error probability. So here you can see that the ASK signal straight away go through the diode and then go through bandpass filter to become a message signal. There is no carrier signal between these. While the other one is called coherent detection. The local carrier wave at the receiving end and the transmitter end will be in phase and same frequency. The error probability will be decreased. However, the system will be much more complex. Here you can see that the message signal will be multiplied together with the carrier signal and go through the low pass filter to filter out the noise and finally become a message signal. And that's all from me. And I will pass to my next team.
I'm Divanandini Nagarajan. Now I'm going to present about bit error rate. Noise or error in digital communication system is measured using bit error rate. Bit error rate is defined as number of bit in error divided to the total number of bit transmitted. Here as an example, there is only one bit is different in receiver bit from the send bit. Using the formula, we can calculate the bit error rate, which is 1/10 equals to 0.1. Other than this formula, we can also define it using signal to noise ratio that equals to 1/2 signal to noise ratio. The bit error rate has to be less than 10 power of -9. As an example, the question states calculate the bit error rate of a wireless communication system at SNR equals to 20 dB. As a solution, the SNR is in dB. Firstly, we convert it using the formula. We got SNR is equal to 100. Then substitute the new SNR value in the formula which consists of SNR. The bit error rate is 5 times power of -4. Energy per bit to noise power spectral density ratio is a normalized signal to noise ratio, so called SNR per bit. EB is the signal energy associated with each user data bit in unit joules. It is equal to the signal power divided by the user bit rate. NO is the noise spectral density in unit joules. It is the noise power in 1 Hz bandwidth. Normalized NSR equals to EB over NO. It is directly measured the power efficiency of the system without regard to modulation type, error, correction coding or signal bandwidth, including any use of spread spectrum.